When we define a function dynamically, what we might say is that function closes over its defining environment. That is to say, that function will identify what data it needs that is not provided as a local variable or must otherwise be a global variable, but is instead provided in the enclosing scope. And it will capture that. It'll capture that by, one, generating load deref bytecodes for the loading and the storing of that variable. And it will create a closure, which is a tuple of cell objects that contain references to the closed over data. You can see here I've passed 1, 2, 3 into this function, and that 1, 2, 3 has been captured in my closure as its 0th cell, and you can see here the cell contents. And in fact, if this is some mutable value, like that, you can see this is actually a reference to that mutable value. If we ask, is the closures cell contents the exact same object as this list? Well, here we'll definitely see they are in fact exactly the same. They are identical. This is a reference to that underlying data. When you look at this, you may say, well, I'm passing in some data and it's getting captured and I'm getting back a function that can operate on that data. That's not altogether too dissimilar from the idea of encapsulation as I see it in typical class-based object orientation approaches. Here you can see a class that we've written which takes some initial state, provides you with some functionality to operate on that state, and in object orientation terms, we would say encapsulates that state. Here you can see we can operate on this. We can call that call method over and over and over, and you can see we can manipulate that state. We can even peek at this thing and peek what that state is. And whether or not we should touch that state object directly or not, well, that kind of comes down to how is this intended to be used. Maybe the absence of an underscore in the naming of state indicates that you're allowed to touch that dot state and you're about to look at it directly. You're allowed to mutate it directly. But whatever the case may be, you can see that we have at least created some object and we've encapsulated that state with some behavior around it, which is not too dissimilar from what we can do with a closure. Here's the same example with use code that looks identical to the use code that we had before, and you can see identical behavior. In fact, a closure is another way for us to encapsulate data and to provide some functionality, some behavior that operates on that data. Now, if we were to look at this entity directly, it wouldn't be as clear that there's some state lurking behind the scenes. We'd actually have to dig into it. And this is maybe one reason why we might choose to use the class-based object orientation versus this closure-based encapsulation. If we were to bring these two examples together, we can see how they are directly related to each other. The use code is identical, and if we look at both of these, we can see in the case of the class-based object orientation, we're just storing that instant state here. This is a slotless class, so we're storing it on this dictionary internal to this object. In the case of the closure-based encapsulation, we're just storing that same data in a closure. And we can see the duality here. In fact, this is a very well-known duality in object orientation. That is to say, objects and closures, for the purposes of encapsulation, are really two ways to accomplish the same goal. For those of you who ever write any JavaScript, you'll see that a lot of JavaScript programmers don't really use the class keyword in JavaScript and instead use the closure style much more frequently. I couldn't give you a strong answer why that is, other than JavaScript object orientation works very differently than object orientation in other programming languages. It's prototypical in nature. And also, JavaScript programmers really like functional programming. I think their preference stems more from desire to do more functional programming and their love of functional programming than any limitations or any differences in the mechanics of how class works in JavaScript. But what you'll see is in JavaScript and a lot of JavaScript code, really the class keyword doesn't show up much. And instead of using that class keyword, they'll use closures in order to accomplish the same goal. Now, when we create a generator coroutine can maintain its local state in between iterations. And so here I have a generator coroutine. And that generator coroutine takes some initial state. And every time we loop over this thing, it can operate on that state if it sees fit. Here I could do something like this. And we could do a couple of next values to see what happens to that state as we go through this. And we should probably yield this state as well so we can see it along the way. And you can see in the generator instances frame, f_locals, we can see the local state for this long-running computation. Well, this seems to be yet another way that we can accomplish the same goal as class-based object orientation and as the closure-based encapsulation. In fact, we can write a variation of the same example using all three approaches. Here, using the class statement, using a closure, and using a coroutine. And if we look at our use code here, that is the way in which we use these three mechanisms, looks identical. From the outside, we might not even be able to distinguish, did we write a class, did we write a function with a closure, or did we write a generator coroutine? Similarly, if we dig into the structure, we can see we're just storing that state in different ways, either on a dictionary associated with the instance of this class, on a closure associated with the dynamically created function, or in the local scope of the long-running computation, the generator instance associated with this generator coroutine. And if we dig into that, we can see the same data is being stored, it's just being stored in different places. If we have multiple ways to accomplish the same goal, a big question that might arise is, which do we choose? Well, there are some thoughts behind why we might choose one or the other, and some judgment as well. Well, if it were the case that we want somebody to be able to dig around in our classes, we want to make these classes relatively transparent to the dir, see what that is, help, dir, see what that is, help approach that a lot of programmers take when they're trying to interact with our tools, with our libraries. We may choose to write a class. Because if we take the class formulation here and we do a dir, we can see the state. If we had other methods here, we could see those methods implemented. We could even implement dir itself to make it much easier for somebody to see that there's just that state there. And we'd support somebody digging around, seeing what they can do, and making use of our code in this fashion. Otherwise, we might require that they read through some documentation rather than just figure it out by live coding. If we did the same thing with a closure, well, look at the dir. It's a dir on a function. This just isn't very indicative of anything, and somebody would have to explicitly look at the underlying closure in order to figure out, oh, there's some state lurking behind the scenes. If we wanted to implement multiple methods on our object, well, it makes sense that we probably want to write a class because a closure approach is going to be a lot clumsier. And the generator instance or the generator coroutine approach is going to be even clumsier than that. Here you can see we have some encapsulated state with an incrementer and a decrementer. And if we want to implement the incrementer and the decrementer, here you can see we can just create instance methods and we're good to go. And if somebody needs to figure out what those instance methods are called, they'll just do a dir. They'll see them here. They'll do a help on that. Hopefully there's some docstring associated with these, and we can see how to use this entity. Let's fix a typo here. Now, if we were to try to do the same thing with a closure, well, we can return two functions. But if we do that, well, this is a lot clumsier because first, the dir doesn't really tell us anything. Actually, let's return this version. The editor doesn't really tell us anything. And in order to invoke the two methods, we have to do index-based access, which is why we could use a named tuple to allow us to do either named-based access, which now is starting to look very similar to what we had with the class, or, of course, if we knew strictly how many different functions were being returned, we could unpack them and then refer to them by name. Whatever the case is, this is starting to get quite clumsy, and it remains to be seen why we're using a named tuple if our goal here is to avoid that class-based object orientation. The named tuple is just a boilerplate elimination tool. Is this object orientation or not? Somewhere in the middle. I think this is probably just about the extremes or the extents of where we might use this closure approach. Probably any further than this, and we should just have written a class-based object. If it's the case that we want to implement the Python vocabulary, then we must write a class-based object because other than employing some boilerplate elimination tool like a context-lib.context manager, the only way that we can interact with the Python vocabulary is by writing these data model methods. So in this case, if we wanted to support things like len, that top-level function, that built-in function, or the getItem protocol, well, it's going to be really, really clumsy to do this with a closure and a named tuple, and we can't do it with just a closure by itself. That is, the class-based object orientation approach is the only way that we can interact with things like the getItem protocol, the len protocol, the context manager protocol. All of these require that we implement some underscore method, either directly or via some boilerplate elimination tool, such as a context-lib.context manager. If we want to hide some data from our end users, well, we should take a big step back and say, are we doing this to help them, or are we doing this to hinder them? And it's often the case that when we're trying to help somebody, we should really ask ourselves, are we really genuinely trying to help them? Are we being as sympathetic as we can to their circumstances? Or are we trying to be antagonistic or coercive in some way? Because if we say we should use the closure in order to hide some data from our end users, and we do this in some coercive or antagonistic way, we're really not going to accomplish much other than making their lives more difficult. We're going to make everything clumsier, and they're still going to be able to dig into the entity that we provide them and figure out how to find or mutate that data. It's just going to take a couple more steps. And so we should not write a closure if we think, oh, this adds safety, this adds control to our program. No, it might add or it might remove some way for us to make a trivial error. But a sufficiently motivated user can still dig into the entities we provide them and still mutate things, or still look at things that they're not supposed to, or still create dependencies on internal details they're not supposed to, that unless we have a good culture of code review, is something which we can't really antagonistic or coercively prevent them from doing. Note that this is not too dissimilar from the guidance that we might have on property. Some people use property in order to create read-only fields, but nothing stops an end user from mutating the underlying thing that the read-only field is reading from. And we can try to make this deeper. We can try and have a dynamically created class where this is closed around the scope here, so they have to dig pretty far. But here's the thing. It's not only that these information hiding approaches really only stymie somebody who's not sufficiently motivated to get around them, but once somebody is sufficiently motivated to get around, there's really just a bunch of DIRs. You know, it's barely an afternoon of work for somebody to dig around. It's probably 5 minutes of work. DIR, what's that? DIR, what's this? DIR, what's this? To create the long chained lookup to figure out, oh, if I go into the class and I go into the property objects fget and I go into the closure of the property objects fget, I can find the cell contents and I can go mutate those, and I can do what I'm actually trying to do that the author of this code is trying to prevent me from doing because they're not sufficiently sympathetic to my use case and the ways in which I might need to break their encapsulation to just get a task done. In all of these cases, we should have just written the simplest code possible and used some sort of code review mechanism, maybe a comment, maybe some feedback in a code review, maybe some special naming like putting an underscore somewhere, and to say, look, we'd prefer that you not do this, but we understand that you're very close to the use case, you're very close to the business use case. Maybe if you need to do these things, you know better than I do. Maybe I should be sympathetic that, please don't, because maybe it's not a good idea. But if you do, well, let's just make sure that we clean it up later. So where should we use a closure? Well, on the other side, judgmentally, or if we use our judgment, that is to say, if it's the case that we feel like it would be helpful to a user to not clutter their view with all the internal details of a class, maybe a closure might be a superior choice. That is to say, in these two cases, we give our end user something that can be called using the call protocol, the open close parentheses. And if our user takes a look at what they're given and they see a class versus a function, well, the class raises a bunch of questions in their head, which are there other instance methods? Are there other protocols? what am I supposed to know, or what am I supposed to do with the internal state? Is that something that I'm supposed to care about? Is that something to look up directly? Is that something I'm supposed to manipulate? And the use of a closure is one subtle way that we can convey to our end users, the users of some API that we provide, you know what? Don't worry about any of those details. All you get is a function. You can call it. That's all you have to worry about. Think about that and then move on to other things that you have to worry about in your life. Here you can see we are being very sympathetic to our users. We're really trying to say, I know that if I give you something that's more complicated, it's going to raise questions. And I know if it raises questions, that's going to distract you. And I don't want to distract you from the things that you need to do. And so what I'll do is I'll give you the simplest possible implementation of some mechanism in order to give you the least possibly distracting thing. When I get a function, the only thing I think about is, how do I call that function? But when I get a class, I think, or if I get an instance of a class, I think, well, should I do a dir? What else is there? What else should I be aware of? What documentation do I need to read? Where might I choose to use a generator coroutine? Well, if I have a heterogeneous computation, we probably don't want to implement this as a generator coroutine if the computation is going to be triggered manually. For example, here we have some class or some class-based object, and we have functions f, g, and h. And if you look at the code, you can see there's an inherent sequencing. That is to say, f has to be called before g, and g has to be called before h. If we call them out of order, some internal state won't be set correctly, and we'll run into some error. And so if we call them in order, everything's fine. But if we change the order here, we get an error. There's a strict sequencing of these operations. When we see that strict sequencing, we might say, well, a strict sequencing is very indicative of a larger computation that has just been decomposed into parts. And in fact, this is not f, g, and h, but this is the f part, the g part, and the h part of a larger computation, which strictly sequences f first, then g, then h, leading us to say, well, we could instead implement this as a generator coroutine. Here you can see a very similar implementation as a generator coroutine, and the use code is not altogether that dissimilar than what we had before. In fact, if we had made object just the .send method, then it would look very similar to what we had before, except note, the three computations we're performing are distinct. Are we doing f, are we doing g, or are we doing h is not visible from the end user code. And if these are very different computations, well, it may not be the case that they're just updating some internal state, but they could be doing something else that's useful. And if you think about how this is going to play out in real code, you're going to see some part of the computation and then a bunch of lines and then some other part of the computation. And here you're going to wonder, well, wait, is that the G part or is that the H part? If this computation is sufficiently heterogeneous, writing it as a generator coroutine is going to make it really difficult for somebody to manually step through the computation, because at any given point in the code, they're not going to be able to say, is this object.send or the next of object, the first part, the second part, the third part? And if it's heterogeneous, then we may very much care which part of the computation we're looking at. However, if we have a single homogeneous decomposition of a computation, that is to say, every pass through this computation is largely equivalent to every other pass through the computation, well, then we may choose to use a generator coroutine, because a generator coroutine provides a very low conceptual overhead compared to a class-style object. Here you can see when I'm given a generator coroutine, I get some iterator. And really all I can do with this, if I call it dir and I see there's nothing there, this is very clearly a generator instance from the fields that we see on the bottom. And I can do a next on it. I can do a send on it. I can do a throw into it. I can do a close into it. Of course, I can do the send only if I send a none value in first. But there's very few things I can do with this. When I call send on this, I can only send one piece of data in, and I only get one piece of data out, which if it's a tuple or something like that, I have to unpack. This is a very simple API. And there's really not much I can do with this entity. So when I see this thing, I can say, okay, this is what I do with it. Let me move on to more pressing questions. I don't have to really wonder what else might be supported, what other mechanism, what other functionality is there. We may discover that providing APIs to our end users through some call unification gives us a very simple API that's quite extensible and gives our end users a lot of choices without creating an API that requires a lot of documentation or a lot of deliberate design or thought. For example, if we had an API and it provided a single callable of one argument, we could implement that API, this is some extensible API of course, as a function generated an enclosure, as a class with a call method, or as a generator coroutine, which unifies the API by providing you with the .send method and also eliminates the first REST modality by pre-pumping this. And in this case, we might see that if our API allows you to take a single callable, where that callable it operates on a single argument, any one of these four entities can support whatever that API needs, and gives you a lot of options. You can write any one of these three, and you can choose to scale what you write to the complexity that you want to impose upon the readers of your code.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.